Some fun graphing with Desmos in 3 dimensions. So this is a brand new Desmos beta feature, which I was really excited about when I wrote this course. So this is how you enter the 3D beta. I just exited out. I didn't do the quest. But what you can see is because we're graphing in 3D, if I rotate this, this is what we're used to graphing. So here is the 2D plane. This is the XY plane. To create a 3D graph in math, we add a third axis, Z, which basically adds a layer of depth. So I have X is still my width, and Y. So I have like my width and my length with my X and my Y, and then Z is what determines the depth of a function. So when you're graphing in 3D, this is what the axes look like. And so basically you have equations now that are going to be X, Y, and Z. So if I want to graph a plane or a rectangle, I just use X, Y, and Z, and that will graph a plane that's going to intersect. And so right here, you can see that it creates this plane. And it's uneven because I have it set equal to 5. So you can play around with this and look at how it changes the plane. This actually is not this shape. What's happening is I can only see what's in the box. So if I keep extending these planes, they go out forever. But I can make an octagon in my box from using 1. I can make this. I can set X equal to 0, and it puts a line directly on the axis. I can do Y equals 0, and it puts a line directly on the axis. So that's just kind of, and then when you click extend to 3D, that's what makes it graph. So this would be Y equals 0 in 2D. And then if I did it in 3D, it creates that rectangular plane. So you can get different shaped planes within the constraints of this because they would continue forever. But what happens is I can only view a certain portion of forever, which is why I can make different shapes like octagons, hexagons, trapezoids like this. So what's happening is because I'm limiting what I can see, they would extend forever and it would look like a rectangle if I could continue extending it. But fitting in my box, this is what I'm working with. So to graph a sphere, you're going to use an equation called x squared plus y squared plus z squared, and that's going to equal the radius squared. So this is a sphere that has a radius of 2, and so if you look at where these numbers are, the top of my sphere is at 2 and the bottom is at -2, so my radius length is going to be 2. I have the plane y equals 0 in there right now, and I just clicked extend to 3D. And now, do you see how this is cutting through the sphere right dead center? This is like the idea of the equator or the prime meridian because it's going directly through the center of the sphere, which means if I was to trace in 2D, the circle that's there, and I'm not sure if I can graph this, but I'm going to give it a whirl because it sounds fun. Let me see what that does. So if you were to trace this circle right here, it would become the great circle. Oh, that's interesting. That's not what I wanted to do. But if you were to trace around the outer edge of this sphere, the circle that you trace would be called a great circle because it passes dead center through the sphere. Now, as I get a little more proficient with my spheres, I can actually start shifting the sphere around, which means that I have to shift my great circle because now this is not cutting directly in the middle. Do you see that little blue line right here? That means I've shifted, and look, the sphere is no longer evenly cut in half. It's kind of a little oddly proportioned. And so I would have to adjust my great circle, and that's kind of a fun process because you're never sure exactly what you're looking at for a great circle. But if I shift to x equals 1, it does look like I, in fact, hit, again, dead center. So there's a relationship between the great circle equation and the shifting and the sphere equation. And so what you're going to do this week is you're going to play around with this and give me different configurations of shifted spheres with a plane that cuts it directly in half, forming a great circle. And again, remember, you just trace the outside of the sphere, and the 2D circle that's traced onto that plane is the great circle that happens there. So it's like you're cutting an orange in half, pulling them apart, and then that surface around the inside of the orange, or where the rind is, that's the great circle. And so that's kind of a look at this in 3D. I'm going to also post some apps for you guys to look at, to shift, to get a feel for how this changes, because the idea of a great circle is really this entire central piece to what spherical geometry is. So we really have to nail the understanding of great circles because we utilize them in a lot of different ways.